The ABC of the Universe. The sixth talk in this series is given by Professor Martin Ryle of the Mullard Radio Astronomy Observatory at Cambridge. He calls his talk The Limits of Perception.
Let me start by going back to something that's familiar to you by this time, from the earlier talks in this series and perhaps to your own eyes. If you go out on a clear night, you can usually see the broad band of the Milky Way running across the sky. You'll remember that this is an edge-on view of the flat disk of our own galaxy. Its light is made up from millions of distant stars distributed throughout the whole of that disk. But the brightest stars, unlike the Milky Way, are spread more or less uniformly across the sky. This is because brighter stars are comparatively close to us, and so we see them when we look towards the top and bottom of the galactic disk, as well as when we look towards the edge or centre of the galaxy. If, instead of looking at the visible stars, we scan across the sky with a radio telescope, we again find a band from which the radio waves are strongest, and this band corresponds in position with the Milky Way. But we can also detect point sources of radio waves, and, like the bright visible stars, they are spread more or less evenly across the sky. It was because of this similarity that these sources became known as radio stars, although it soon became apparent that they are not in fact stars at all. The recognition of what they really are has presented us with one of the most intriguing astronomical problems of the last 10 years. Some of the sources are situated close to the disk of the Milky Way, and these are clouds of gas representing the remains of supernovae. But most of them are evenly distributed over the sky, and this suggests that, like the bright visible stars, they may all be situated quite near to us. If they were further away, we should expect an uneven distribution. We would expect to see fewer of them when we look towards the top or bottom of the galactic disk than when we look towards the edge or the centre. If, on the other hand, they are further away still, completely outside our own galaxy, we would again expect to find them as we do, evenly distributed. Some of the sources certainly are outside our own galaxy, because they correspond in position with the nearest of the external galaxies. But most of them cannot be related to any object we can see with an ordinary optical telescope. But in 1950, one of the most intense of the radio sources was identified with an extremely faint and distant galaxy in the constellation of Cygnus, at a distance of 500 million light-years. Another source was located as an even fainter galaxy in the constellation of Boötes, at a distance of 4,500 million light-years. Both of these galaxies must give off radio waves with an intensity about 1 million times greater than that of our own and the nearby galaxies. This means that we have found an entirely unsuspected type of radio source, so powerful that quite different processes must have been going on inside them. But what can we say about the nature of most of the radio sources? Even though very careful searches have been made using the most accurate radio positions, few can be related to any optically visible object. We cannot even decide whether most of them are inside or outside our own galaxy. What we are lacking is a scale of distance, because at radio wavelengths we have no method corresponding to the measurement of the redshift of optical astronomy, and so we cannot tell whether we are observing weak sources which are comparatively close to us, or powerful sources at great distances. Now we can of course see whether any of the types of sources which have been identified optically could explain our radio observations so far. It is easy to show that the majority of sources cannot be the remains of supernovae, because if they were, the band of the Milky Way would be about 100 times as intense as it is. Nor can we account for them in terms of galaxies like our own and the Andromeda Nebula, because we find that there are many sources much more intense than those associated with the brightest visible galaxies. We would also expect many of them to appear much larger in the sky than they actually do, if they were galaxies like our own. It is clear that normal galaxies as radio sources can only be observed to quite small distances, and they can only account for a few percent of all the radio sources which we can detect. If, on the other hand, we suppose that most of them are like the very powerful sources which have been found in the constellations of Cygnus and Boötes, then we find that we have a possible interpretation of all the observations. The source in Boötes is at the limit of detection of the great 200-inch telescope on Mount Palomar, yet it is easy to detect with a radio telescope. Similar sources at greater distances would still be easy to detect with a large radio telescope, although invisible optically, that is, to the eye and on photographs. We can also calculate that the sizes of such sources in the sky would be similar to what has been found in practice. From these and other arguments, it now seems clear that most of the so-called radio stars that we observe are in fact outside our own galactic system, and that they belong to an extremely rare class of galaxy, of which there is perhaps only one in every 10 million normal galaxies. These radio galaxies must give out radio waves about 100,000 times more powerful than normal. We don't yet understand fully what causes this very powerful radio emission. As Professor Henry Brown said, most of the radio waves from our own galaxy are believed to come from the movement of high-energy electrons through weak magnetic fields in the gas between the stars. In these powerful radio galaxies, there must be more high-energy electrons and stronger magnetic fields than in normal galaxies, and this additional energy must come from somewhere. One possibility is that radio galaxies really represent collisions between galaxies. Although the chance of such an encounter happening to any particular galaxy is very small, we have seen that only one galaxy in every 10 million is a strong radio source. Now, in a collision between two galaxies, it is unlikely that any stars will collide, because the stars only occupy a very small fraction of the total volume of each galaxy. But the interstellar gas of the two systems will be heated to a very high temperature by the collision, a result which is indeed found for the radio galaxies in Cygnus and Boötes. At the same time, electrons might be accelerated to high energies by a mechanism like that used in some of the large nuclear accelerators. Another possible theory is that early in the life of a galaxy, the rate of supernova explosions may be very much greater than we observe now, and that for a period of perhaps 10 million years, these explosions might occur sufficiently often to provide enough high-energy particles to account for the very powerful radio emission. Well, we don't fully understand how such powerful radio sources come about, but their existence does allow us to investigate problems of the greatest interest. This is because, with a very large radio telescope, we can detect these sources at distances far greater than can be reached with the largest optical telescope. Now, the radio source in Boötes has been found, from the observations with the Palomar 200-inch telescope, to be at a distance of 4,500 million light-years. And if, with our large radio telescopes, we can detect sources perhaps 20 or 30 times fainter, many of these must be at nearly double this distance. Why are we so interested in extending our observations to greater and greater distances? The reason is that this is the only way we have of exploring the life history of the universe as a whole. If we can observe a galaxy at a distance of 4,500 million light-years, the light or radio waves, which we are now receiving, were emitted 4,500 million years ago. The picture we have is therefore of a galaxy 4,500 million years younger than our own. So, by comparing observations of distant and of nearby galaxies, we have the possibility of detecting any large-scale changes which may have taken place in the structure of the universe. If, for example, we suppose that the expansion of the universe, as indicated by the redshift, is the consequence of an initial explosion, and that all the galaxies were born after this event, then, because of the time taken for their light to reach us, the most distant galaxies will appear to us younger than those near to us. If we extend our observations to more and more distant galaxies, we should expect to find a progressive decrease in their apparent age. We should also expect the more distant galaxies to appear more closely packed together, because we should be observing them at an earlier stage in the expansion. On other theories of the universe, different results would be expected, and so special observations aimed at distinguishing between the different theories have been devised. Much of the time of the great 200-inch telescope on Mount Palomar has been taken up in programs of this type. The observations must be made out to the weakest detectable galaxies, and the interpretation of the results is complicated by the uncertainty in the way in which galaxies may change with age. As a result of this, it's been difficult to reach definite conclusions, although the most recent results support the idea of a universe that originated in an initial explosion. The difficulties arise simply from the fact that the most distant galaxy which has been detected with the 200-inch optical telescope is observed at an age, on an explosion model, already about half that of our own galaxy. Unless very marked changes have occurred in the last 4,500 million years in the life of our galaxy, it is likely to be difficult to distinguish with certainty between many of the possible theories. But the discovery of these powerful radio galaxies and the recognition that most of the sources observed with a large radio telescope must be equally powerful and so observable at great distances, this may now provide us with the opportunity of reaching much more definite conclusions. The greater range of detection allows us to reach back further in the life history of the universe, to times when the galaxies may be only about 1/5 of the present age of our own galaxy. We should then expect to find larger differences in the predictions of different theories, and although the radio observations are likely to be less detailed than the optical ones, the effects to be investigated should be more marked. The present preliminary results of such radio observations support the idea of a universe which originated in an initial explosion. What we now need are more detailed observations with larger radio telescopes, so that we can extend the exploration to still greater distances, and so that we can learn more from the nearer sources about how the radio emission is produced.
That was the 6th talk in the BBC series, The ABC of the Universe. It was given by Professor Martin Ryle of Cambridge.